So yesterday we were dealing about the linear regression. We learned how we draw scatter plots, how we draw linear regression, how we can compute the correlations, and how we fit the linear regression model. If you remember about the lecture of Professor Rajiv Pandey sir, they have told you about the assumption of normality. और जितना मुझे रिमेम्बर है उन्होंने कहा था कि पहले आप नॉर्मेलिटी चेक करिए, देन आप एनालिसिस को परफॉर्म करिए. ठीक है. सो नॉट ओनली लीनियर रिग्रेशन एंड every statistical techniques deals with certain assumptions, and that is there is not only assumption of normality, there are a number of assumptions. In same manner, multiple linear regression also deals with some assumptions. These assumptions are: first one, that dependent and independent variables all must be continuous. If they are not measured on continuous scale, if data is collected using MCQ type questions or close-ended questionnaire, then do not run regression analysis on that. Number two, assumption of linearity. We have checked the assumption of linearity using the concept of scatter plot as well as the concept of correlation. Third assumption is assumption of normality. Fourth assumption is assumption of homoscedasticity, and fifth one is assumption of multicollinearity. Today we will discuss what these assumptions are and how we check using SPSS, and if there is certain technique in SPSS available to deal these processes or these assumptions, then we will also discuss or cover that topics. So dependent and independent variables must be continuous. You can check this assumption by seeing the data or by considering how the data is collected. If data is collected using any specified scale, or it is measured in terms of, it can be measured in terms of decimal, then you can assume that it is continuous, and you can run or apply linear regression on that data set. If data is collected using close-ended questionnaires or MCQ type questions, or they have categories, then don't run regression on that. If data is on categories, then it will be preferable to use logistic regression, which will be discussed tomorrow. Second is assumption of linearity, which means that dependent and independent variables must be linearly related. So check whether the variables are linearly related or not with the dependent variable. We use scatter plot and we use correlation coefficient. So we have learned these topics yesterday. How we draw the scatter plot and how we calculate the correlations. Now third one is assumption of normality. Assumption of normality indicates that error term must be normally distributed. But error comes only after fitting the linear regression or after running the linear regression. You cannot obtain error before running the analysis. So it is not genuine to test the normality of the error term. So it is preferable to use to check the normality of dependent variable. So that you can say that this assumption is similar to the assumption that the dependent variable should be normally distributed. So first we check the normality of the dependent variable, then we perform the linear regression analysis. In SPSS, we can use Kolmogorov-Smirnov test, we can use Shapiro-Wilks test, or we can use QQ plot and PP plot in SPSS. There is another technique which is used but not gives a genuine result, is plotting the normal curve on the histogram. But it is preferable to use Shapiro-Wilks or Kolmogorov-Smirnov test instead of using normal curve on histogram. So for obtaining the Kolmogorov-Smirnov test or QQ-PP plots for the test of normality, we go to analyze in SPSS. Then we go to descriptive statistics. There is an option of explore. Click on that option. We are using same data sets which we have taken yesterday. So there is no problem for performing the analysis. Everyone will have the data set. Then on clicking the explore, you will get this dialog box open. It is asking dependent list, vector list, and label case by. Dependent list is continuous variables. Vector list is categorical variables. And label case by, if you want to divide your data into two or more parts, then you can use option label case by. Since we are dealing with continuous variable and our variable is dependent variable, for which we have to obtain the normality. So we put the variable in the box of dependent list, that is in this box. Then we click on the option plot, that is on this option. When you click on this option, it will open another dialog box which has certain plots. Factor level, one is box plot, second one is descriptive, third one is normality plots with S. So in this, you have to, by default, it check stem and leaf plot, and box plot will be set as factor level together. So you have to uncheck the stem and leaf plot, and in box plot, you have to select none, and then click on normal plots with test. That is here. Then click on continue. Then it will go back to the explore option. Then click there on OK. Let us form the normality test using the data set. So kindly open the data set car sales and prepared in your laptop or in the systems you are using, online as well as offline. Dataset is open. Then go to analyze. There is option descriptive statistics. Then in descriptive statistics, there is option explore. Click on that option, explore. Then it will open dialog box like this, explore. Select your dependent variable and put in the dependent list. Then click on plots. You can see by default, box plot is vector labels together. Make it none. There is descriptive, stem and leaf is by default check, uncheck it. And select normal plots with text. That is check on the normality plots with text. Then click on continue. Now, when you continue, you see at this place of the dialog box, there is display both statistics and plots. We have selected or manage the option of plots. So here we click on plots. It will give only plots. You can see statistics button is done. Okay, so it will not calculated any of the statistics. Then click on OK. So here you can see that p-value for Kolmogorov-Smirnov test statistic, that is test for normality. If significance comes out to be larger than 0.05, we say that our data is normally distributed for Kolmogorov statistics as well as for Shaffer-Wilks statistics. If it comes out to be less than 0.05, our data is non-normally distributed. So in our case, the test is showing that our data or our dependent value is non-normally distributed. In same manner, you can interpret a QQ plot or PP plot. Let us consider the QQ plot. If these points are concentrated on this diagonal line, then you say that your data is normally distributed. If these are deviating from the line, you said that data is non-normally distributed. That is, आपके सारे points करीब करीब इस लाइन, जो डायगोनल लाइन आपको दिख रही है, इसके ऊपर आने चाहिए. अगर इसके ऊपर नहीं आ रहे हैं, इससे डेविएट कर रहे हैं, तो आप कहेंगे आपका डेटा नॉर्मली डिस्ट्रीब्यूटेड नहीं. इन सेम मैनर इन पीपी प्लॉट, ऑल द प्लॉट्स मस्ट बी कंसंट्रेटेड अराउंड द हॉरिजॉन्टल लाइन. अगर इस हॉरिजॉन्टल लाइन पे आपके डेटा कंसंट्रेटेड नहीं है, तो आप कहेंगे आपका डेटा नॉर्मली डिस्ट्रीब्यूटेड नहीं है. So in both the plots and both the tests are saying that our data is non-normally distributed. Now the data is non-normally distributed, then what we have to do? हमको क्या करना चाहिए? डेटा को या वेरिएबल को नॉर्मल बनाने के लिए हम सर्टेन ट्रांसफॉर्मेशंस यूज कर सकते हैं. जनरली यूज होने वाले ट्रांसफॉर्मेशंस लॉग ट्रांसफॉर्मेशन एंड बॉक्स कॉक्स ट्रांसफॉर्मेशन है. बट इन SPSS, log transformation is available, but box-Cox transformation is not available. If you want to apply box-Cox transformation, then you have to use some other software. How we apply the log transformation? We will go to transform. We go to transform. Then there is another option, an option, compute variable. Click on that. Then in compute variable, there is two options, target variable and numerical expression. So target variable, that is, you want to generate a new variable which have considered the log of dependent variable. You can give any name to this variable. I am giving name it to ln underscore resale. Okay. Fourier resale value is given in the variable resale. So I am giving it the name ln underscore resale. ln means natural log of resale value. If you want to give a specification, you can click on types and type and label. Okay. So label, we can write natural log of Fourier resale value. Okay. Click on continue. Now in numerical expression box, we will type the expression. We can directly write function ln, then within bracket the name of variable. Okay. If you have certain doubt what command should we use, what function we want to use, there is a problem, you cannot remind the name, then click on here function group, click on all. Whatever functions are available will be displayed here. जो भी आपके functions हैं available, सब आपको यहाँ पे function and special variable में दिखेंगे. You can select ln from here. Okay. If you click on any of the function, you will get what it is representing. Okay. Like if you click on CDF normal, then it is showing that what CDF normal is representing. In same manner, if you click on ln, it will show that it is representing the numerical value and returns the natural log of the number. You can click on this arrow. Okay. Just click on this arrow. Function will comes out to be in numerical expression. Then there is a question mark within the expression. Replace this question mark by your variable. That is, select variable from the variable list and click on else. Okay. Then click on OK. When you go to your data set, in last, you will get the variable ln resale. Everyone has got? What name you have given, check that name. Okay. But if SPSS is showing some error, then what error we will discuss. Any problem? If in data you cannot see, you can go to variable view. In variable view, you can easily obtain that there is variable generated. Okay, it will always displayed in the last. Now you can check the normality of this also. Now I am giving 5 minutes to you. Check the normality of this variable, whether it is normal or not. Yes. Which variable we are considering as dependent variable? We check the normality of that. Okay. Okay. There is no non-parametric analog is applicable with respect to linear regression. We have to go for the transfer. Okay, one online participant has asked to repeat the process of computing the variable or calculating the log. So for that, we go to transform, then go to compute variable. Give any name to your variable in the target variable. Whatever name you want, you can provide. Okay. Suppose I am giving ln1 underscore reset. Then click on type and label. You can describe here what the variable is representing. Like natural log of 4-year resale value. Then click on continue. Then click on function group at this place, and on that you click on all. and there is a function log. There are two logs, one is LG10 and ln. So we are going for natural log, that is ln. Then select ln and click on arrow, this arrow. It will put ln in numerical expression with a question mark. Question mark is for what variable you want to use. Put that variable in place of question mark by selecting it. Just select here the variable, click on arrow, it will replace the question mark. Then click on OK. In data set, new variable will be generated. Here you can see on the yellow line that your variable ln1 underscore resale is generated. Now, not necessary. Have you checked the normality of this log variable? What is the result? Not normal. It is not necessary that after applying the log transformation, it would become normal. So you may apply some other transformation. There may be another reason that your data consists of outliers which are causing the non-normality of data. So first you can remove that outliers and then perform the test. But I am not going to discuss this process. For that purpose, you can construct the box plot. Box plot will identify what outliers are in your data set. Remove and then check the normality of the data. Maybe your data become normal. If it is not becoming normal, then apply log transformation. If log transformation is also not making it normal, then apply box cost. Most of the cases when you apply the box cost transformation, you will get normal data. Okay. Now we come to second assumption. That assumption is assumption of multi-collinearity. Assumption of multi-collinearity states that the independent variables must be independent of each other. Or you can say that predictors must be independent of each other. Multi-collinearity exists when you are using more than one independent variable. If you are using single independent variable, then there is no meaning of multi-collinearity. And that is when you are using multiple linear regression, you have to check the assumption of multi-collinearity. There are several methods using which you can identify the multi-collinearity. You can give an idea that multi-collinearity is existing by using correlation matrix. We have constructed the correlation matrix yesterday. If you have saved it, then you can see that there is a problem of multi-collinearity. Price is highly correlated with engine size or horsepower. Okay. There is another method of identifying that multi-collinearity is existing. If the value of R square, that is coefficient of determination, is high and very few variables are significant. A better idea is provided with the help of variance inflation factor, which is also known as VIF. If VIF, minimum value of VIF comes out to be larger than 2, then you can say that the problem of multi-collinearity is existing in the data set. So we have studied how we perform the correlation analysis or how can we get the correlation. Okay. So in slides, we are discussing only how we get VIF or how we get other things. For checking the multicollinearity, go to linear regression as you have gone. Then select the dependent and independent variables. Then click on, sorry, then there is option statistics. Click on that. Okay. Then there is option part and partial correlations and collinearity diagnostic. Check on that. Then click continue and click on OK. So first, for performing the collinearity diagnostic, first we are going to see the correlation table. Let us make the correlation. Go to correlate and bivariate. Okay. Put the independent variables in the list of variables, not the dependent one. Okay. Now we are interested in the linear relationship or relationship between the predictors or independent variables. So put all the independent variables in the box of variables. Then click on OK. So here you will see that engine size and price correlation coefficient is 0.627. That is moderately correlated. Price is highly correlated with horsepower. Correlation is 0.840. And when we are using a number of variables which are highly correlated, one of them will comes out to be significant and other will comes out to be insignificant. Similarly, you see curve weight, fuel capacity and fuel efficiency. These are also moderately correlated. So high correlation indicates that independent variables are linearly related or problem of multicollinearity exists. But we cannot sure about moderate correlation whether variables are exactly correlated or not. So for that purpose, we use the concept of VIF to make ensure that multicollinearity is existing or not. For the purpose, we go to regression. Then there is an option of linear. Click on that as we perform linear regression analysis. Then there is Fourier resale value. Make it as dependent variable and take all the other variables which we have taken yesterday, like price in thousand, engine size, fuel capacity, fuel efficiency, etc., as independent variable. Then click on statistics. There is option part and partial correlation and collinearity diagnostic. Click on these options and click on continue. Then click on OK. Now you can see that the R square is 0.947. That is, variation in dependent variable can be 94% variation in dependent variable can be explained with the help of independent variable. That means value of R square is high. Now, when we go to the table of coefficients, you can see that in significance, price is 1000 is significant, width is length is significant, and curve weight is significant. That is, only 3 variables out of 9 are coming out to be significant, and remaining 6 are insignificant. That is, 6 variables are not contributing in the mod. So you can say that problem of multicollinearity is existing. Same you can judge with the help of VIF. If you see that the minimum value of VIF, it is 0.337. So you can interpret it that problem of multicollinearity is existing. Now, where the problem of multicollinearity is exactly existing. So for that purpose, we use partial correlations. What are these partial correlations? Simple correlation is a measure of linear relationship between any two variables. But that relation is affected by the presence of other variables also. That is, if you are making changes in price is 1000, it is related with horsepower. Then horsepower will also be changed. Whether you are considering it as independent or dependent, it doesn't matter. If these are related, if you are changing one variable, other will also change. So change in horsepower will cause a change in prices 1000. Similarly, change in engine size will cause a change in price in 1000. So here we try to remove the effect of these variables. That is, if we keep other variables constant, then what is the correlation between two variables? That is obtained with the help of partial correlation. Okay. Similarly, there is one more thing, condition index, which is used for explaining the problem of multicollinearity. If condition index comes out to be larger than 10, then problem of multicollinearity is existing. So here you can see first is 1, second is 5, and third one become 11. And last one is 146. So you can say that the problem of multicollinearity is also existing using this criteria. Similarly, if first eigenvalue comes out to be very, very larger than other eigenvalues, then also you can say that the problem of multicollinearity is existing. So you have four, 1, 2, 3, 4, 5 methods for the detection of multicollinearity. Number 1, by seeing the table of correlation coefficient. Number 2, by using a concept R square is high, but very few variables are significant. Number 3, variance inflation factor. Number 4, eigenvalue. And number 5, condition index. You can use any 5 of these, but it is better to use VIF, eigenvalue, or condition index. It is better if you make the judgment on the basis of these 3 measures, because the simple correlation is affected by the presence of other variables. So we try to ignore the correlation coefficient as a measure of multicollinearity. But it gives an idea that multicollinearity may exist. Whether it is exactly existing or not is judged by variance inflation factor, VIF, or condition index. Now, the next assumption of linear regression analysis is it homoscedasticity, or you can say assumption of heteroscedasticity. It tells that the error variance must be constant. So, for checking this assumption, there is no specified tool is available in SPSS, but we can check using SPSS. There is no option while performing the regression analysis that you can judge whether homoscedasticity is present or homoscedasticity is absent. Or you can say whether data input heteroscedasticity is present. For the purpose, while performing the regression, we use save option. Okay, there is button of save here. When you perform the regression analysis, you have seen certain options here. One was statistics, other was model, and there is third one is save. Using that option, click on that save, you will get this dialog box open. When this dialog box is open, click on unstandardized predicted value and you can select any of the residual. Generally, it is preferable to use unstandardized or standardized residuals. Okay. Then click on continue. And then click on OK on the regression dialog. Just click on save and click on unstandardized and residuals unstandardized predicted value. Then click on continue. Then click on OK. It will generate two variables. You can see here PRE1 and RES1. PRE means predicted value. RES means residuals. So two variables are generated. One is predicted value of Y, other is residuals. If you remember that Rajiv Pandey sir has shown a slide in the last, value of Y, value of X, then predicted value of Y, then residuals, and show that if you put the value of X in the model, you will get predicted value of Y, and you subtract predicted value from the original value of Y, you will get the value of residuals. You have not to do this. By default, SPSS done on its own and give you predicted value as well as residuals. Then to detect the homoscedasticity, we make the scatter plot between square of the residual and predicted values. So for computing the square, we go to transform and then go to compute variable again. Then dialog box will be open. Give any name in target variable. Then write expression. We have to square, make the square of residual. So write it as residual into residual. Then click on OK. It will generate the new variable square of residual. Then make the scatter plot between square of the residual and predicted value. Let us do it first. Go to analyze, then on regression, select option linear. It will open this dialog box. If you have not clicked on the reset button, whatever model you have applied will also representing here. Okay. You can see here it is showing all the independent variables as well as dependent variables. Then they go to option save. Here it is save option. Click on that. On clicking, it will show this dialog box. Select unstandardized predicted value and unstandardized residuals. Then click on continue. Then click on OK. So you can see that regression analysis is performed. Now go to your data set. Every variable generated will always be represented in large. So you can see that PRE underscore 1 and RES underscore 1 are generated. PRE, if you are not understanding what it is representing, expand the column of label. Here you can see that PRE1 is unstandardized predicted value. RES1 unstandardized residual value. Okay, it is already mentioned here. Then go to transform and compute variable. Whatever you have earlier performed is showing here. Click on reset. Okay. When you click on to reset, all the expressions will become hidden. Now write here SQ underscore residual. Yeah, RES underscore. Okay. If you want to define the label, write here square of residuals. Then put residual. Click on this star button. Then again put residual. It will make the square of the variable. Then click on OK. When you click on OK, you will get that SQRES underscore 1 is generated. Hmm? I am repeating the step. Go to transform, go to compute variable, give name to the target variable, then go to type and label, write square of the residuals. Then in numerical expression, put residual, then click on star button, then again put the residual in numerical expression. Okay, if you are not getting where the variable name is, right click on this part and click on display variable name. By default, it display the name label of the variables. So your variable is RES1, put RE1 S underscore 1 in numerical expression, then apply multiply sign or star sign, then again put RES underscore 1. Then click on OK. It will generate the square of residual. Then make the scatter plot between square of residual and predicted values. That is, go to graph, legacy dialog, scatter. Then select option simple scatter. As we are using only two variables, so we can apply simple scatter. Then click on define. Put square of the residual on y-axis and predicted value, that is PRE_1 on x-axis. Okay. Now click on OK. It will show you the scatter plot of square of residual and unstandardized predicted value. If the shape of the scatter plot comes out to be parallel to x-axis, then you say that variance is constant and assumption is fulfilled that your data is homoscedastic. If it is deviating from that parallel and representing some pattern, one pattern may be band of lines, that is linear relationship, maybe shape of some curve, maybe takes shape of some funnel, then you say that problem of heteroscedasticity is existing in your data. So I think my data is showing the shape of funnel. This and this. All the data is concentrating within the funnel. So this data also includes the problem of heteroscedasticity. Okay, is it clear? There is another method for detecting the heteroscedasticity, that is correlation between the residual, square and predicted value. So for that purpose, we go to analyze, correlate, bivariate. Put square of the residual and predicted values in the variable box. Then click on continue. Or you can say click on OK. So here you can see that the correlation is 0.419. That is moderate correlation is existing and which is also significant. So you can also see that this measure is also showing that problem of heteroscedasticity is persisting in your data set. Is it clear? Now, how can we deal with the problem of multicollinearity? There are several methods to deal with multicollinearity. One is by using the method of selecting best regression equation, among which there is forward selection method, backward elimination method, or stepwise regression. Another method is performing the factor analysis, which will be covered in next lecture. You can apply the factor analysis, get the linear combination of the variables which are uncorrelated with each other. Then on these uncorrelated variables, you can perform the regression analysis. So I am not going to deal with factor analysis, but we are going to deal with this one, that is selection method. For that purpose, go to regression and linear. Now here, put the dependent and independent variable as it were. There is a method, there is option method. Click on that at this portion. Here you can see stepwise, backward, forward. Let us take forward selection method. Forward is for forward selection method, backward is for backward elimination method, stepwise is for stepwise regression, which is mixture of forward selection as well as backward elimination. Then click on OK. Let us take one more options, R square change. Okay, click on that. Go to statistics. There is option R square changed. Click on that. Then click on continue. It will deal with two things when you are applying selection methods. It is dealing with the problem of multicollinearity, and somehow problem of multicollinearity is removed. Also, it is using the concept of model building, that is increasing variables one by one when it is necessary. If it is not necessary to include the variable in the model, it will not include that value. Then click on OK. So first we see the table of variables entered or removed. Here you can see model 1, 2, 3, 4. That is, it is providing 4 different models to you. If you are using entered method, you will see that you are getting only one model. Okay, when you are using enter method. When you are using selection method, you are getting a number of models. Maximum number may be equal to the number of independent variables. So it may be one, it may be maximum number of variables. So in second, variables entered, that is at which stage which variable is entered to the model with previous one. That is, if in model 1 price is 1000 is included, in model 2 length is included. That is, model 2 include price in 1000 along with length, not only length. First model includes only price in 1000. Second model will include price in 1000 and length. Third model will include price in 1000, length and curve weight. And fourth one will include price in 1000, length, curve weight and fuel capacity. Further, inclusion of other variables is not necessary as per the concept of SPSS. So after fourth, it is not generating the fifth or other models. Here is variables removed. In forward selection method, you will never get any entry in this column because it is selecting, but it is not removing. In method, you can see the criteria. Probability of F to enter less than equal to 0.05. So for the variable for which the p-value comes out to be less than 0.05, on the basis of test performed on the back end, it will not be shown to you. It is performed on back end. So for which variable significance is less than 0.05 and it is minimum, that variable is entered first. And after that, among remaining for which it is minimum, then that will be entered on next step. Now we come to second table, which is model summary. Here you can see that in first model, R square is 0.912, adjusted R square is 0.911. In for first model, change in R square is not important because it will be equal to R square. In second, R square will become 0.935. That is, there is an increase of 0.23. Same thing, you can see that R square change, it is showing 0.023. That means that is an increase of 0.23% in explanation. And if you see the significance of this, then this change is significant. So you can keep both the variables in the model. Similarly, in third model, R square is increased by 0.03. That is 0.3%. So an increase of 0.3 or below 1% is not necessary. So you can say that you can deal with only two variables, or if you want, you can put all the four variables in your model, because the change is significant whether it is small. Okay. Change is small but is significant, so you can put all the four variables in the model, or you can say 2 seconds is sufficient. After that, change is very, very small, we are not going to consider it. It depends upon whether you accept with model with two variables or you accept model with four variables. Then it is ANOVA table for all the four models. All the four models are significant. If you are including two variables in model and you are saying that two variables are sufficient, we are not going for third and fourth, then select the ANOVA table of model 2 and represent only this one in your analysis. Okay. If you are think that it is sufficient to include all the four variables, then represent the fourth model table. Okay. It is giving you our four options. It is upon you to decide whether you are going with model 1, model 2, model 3 or model 4. Which model you are selecting, use the ANOVA table of that model only. Now, it is a table for regression coefficients. If you will check the significance, in each model, all the variables are significant. Because insignificant variables are not included in the model. So in last week, I am dealing with 4 tables. So you can see that all the 4, price in thousand, length, curve weight, and fuel capacity are included in model. Now it is diagnostic analysis. We are not going to deal it with. Okay, is it clear? Similarly, we can check what the backward method gives. Okay. We have performed the regression analysis. Now we select option backward instead of forward. Then click on OK. Then here you can see in model 1, all the variables are entered and no variable is removed. That is, in backward elimination method, it starts with complete model. That is, model including all the predictors in the model. Then it removes the variables one by one. In first step, it is removing weight. In second step, it is removing horsepower. In starting, we have 9 variables. In second variable, width is removed. That is, we have 8 variables. In third step, horsepower is removed. We have 7 variables. In fourth, wheelbase is removed. Now we have 6 variables. Similarly, at last stage, 5 variables are removed. We have 4 variables in the model. Similarly, it is showing the change in R square. Again, you can see that when we have entered the variables using forward method, R square was increasing. Now we have eliminating the variables one by one, R square is decreasing. And yesterday, as I remember, I have told that we increase the number of variables, R square will increase. Similarly, if we decrease the number of variables, R square will decrease. Okay. But if you see adjusted R square, it is not decreasing too much as compared to R square. And at every stage, the change in R square is insignificant. That means removal of variable is justified. You can remove that variable from the data. If change comes out to be significant, then you cannot remove the variable from your model. So in this situation, our final, that is sixth model, is best. You can take first model also, but in general, it is a rule that model with higher R square and a smaller number of variables is preferable. Okay. So where R square 0.942 is high, or 0.944 is high R square, and it has only 4 number of variables. So you can consider it as suitable model for your data. So we use ANOVA table for model 6. Similarly, coefficients, 6 model coefficients will be considered, and you can see that all the coefficients are significant. If in first model, you will see that price in 1000 is significant, but engine size, horsepower are insignificant. So it is removing insignificant variables one by one. And in final model, you are getting only significant variables only. Now, yesterday I have asked one question in the last, as I remember. The variables which were insignificant in the model with 8th variable, when we include price in 1000, insignificant will become significant and significant will become insignificant. Why it is that? Answer is that it is happening due to existence of multi-collinearity. If you have remember, I have constructed the table of correlation. Horsepower was highly correlated with price in 1000. Similarly, engine size was correlated with the price in 1000. So these will become, when price in 1000 is included, these will become insignificant. Okay. And again, if you will see that we have final model, price in 1000, length, curve weight, and fuel capacity. There are 4 variables. Now we construct the correlation table of all the variables and see what is happening for these 4 variables. Okay. We have in the model price in 1000, length, curve weight, and fuel capacity. Now in the table we see price in 1000, Fourier resale value highly correlated. What about length? 0.027. This shows that it is very slight, it has very slight correlation with Fourier resale value. But model is including it. Why? When it has no correlation with Fourier resale value, then why it is occurring in the model? Similarly, we have two other variables, curve weight and fuel capacity. Let us make a check. Okay. Curve weight is somehow correlated. Curve weight and fuel capacity is also moderately correlated with Fourier resale value. So they may appear. Again, horsepower and engine size are moderately correlated and have higher correlation as compared to curve weight and fuel capacity. But these are ignored from them. Why it is happening? It is happening due to problem of multicollinearity. This high correlation is occurring due to the price in thousand. How we will check it? Whether I am saying correct or not. Go to correlate. There is option partial. Okay. Partial correlation adjusts the effect of other variables. That is price in thousand, engine size and horsepower are highly correlated. If we check the correlation of engine size with Fourier resale value after removing the effect of price in thousand and horsepower. That means जो वेरिएबल उसको इफेक्ट कर रहे हैं उनके इफेक्ट को अगर हम हटा दें तो व्हाट इज द कोरिलेशन बिटवीन हॉर्स पावर एंड फोरियर resale value? Let us make a check. For that purpose, put Fourier resale value and horsepower in variables. Okay, and price in thousand and engine size as controlling variable. जिनके इफेक्ट को हमें रिमूव करना है, that are taken as controlling cost. Then click on OK. Now here you can see. After the removing the effect of engine size and price in thousand, what is happening? Sorry, after removing the effect of price in thousand and engine size, horsepower is not linearly related with, or you can say uncorrelated with Fourier resale value. It has a correlation of 0.059, which is positive and very slight and is insignificant. So you can interpret that horsepower is not linearly related with Fourier resale value. Okay. Similarly, we can make a check of length. Instead of horsepower, we are including length and putting all the other variables as controlling variables. Okay. Then click on OK. You can see after removing the effect of other variables, it has negative correlation which is significant with the dependent variables. That's why length is included in the model, whereas highly correlated variables, engine size and horsepower are not occurring in the, because partial correlation is very. Now, if you would like want, you can ask any question. Is there any query? That's why I am showing a rule of thumb that we include only highly correlated variables. But that correlation is also affected by the existence of other variables. Okay. So correlation between length and price in thousand comes out to be smaller. But when we remove the effect of other variables, you can see that it is correlated actually. When we are dealing with multiple linear regression or multivariate data, then always there exists the problem of multicollinearity. So by seeing the correlation table, simple correlation table, we judge the variables incorrectly. Variables is actually correlated with the dependent one, but by seeing the correlation coefficients, we judge that it is uncorrelated. So it is better to use partial correlation instead of simple correlation. Or it is better to use selection method for developing the model.